All right, so last time we were talking about compiling separately. It was very fun, right? We learned that there's a way to do it separately, make the .o files, do that intermediate form, and then link them together, and that's going to let you compile million file projects one day in the blink of an eye. Because if you just change one thing, you'll need to recompile that one new thing, that one changed thing, and then you'll just relink. Linking is fast, all right? But that is a lot of work to do that separate compilation, linking at the end, like to know how much stuff has changed, just figure all that out. Makefiles were the solution, right? They're going to notice when a file is changed and like have all the rules for building it in the most efficient way possible. So that's beautiful. So learn about makefiles, how to create one. It's always like this: a bunch of rules, thing you want, colon, ingredients to make the thing, then you tab over. You give a bunch of terminal commands to eventually create that final thing. All right, so that's where we stopped, and let's finally make a makefile. I never actually made one. Let's make a makefile for our searching library that we did last time. All right, so I'll bring out all the code from last time. Let's see, it's copy lecture 24's everything.cpp into here, and then also the header file. Just the code parts, CPP files and the header files. Okay. And so we know how to compile it separately, like G++-C, searching.cpp, same for main, then link them together with the .o files. Let's make a makefile to do that for us. So a makefile, remember, it's a special file. It's called makefile with a capital M. It's very weird. We're going to make a makefile, and we're going to give some rules to build the things that we want. Okay? So I got these files. Let's put them at the bottom here. I got main.cpp and searching.cpp that I need to turn into .o files first. Okay, so I need some rules for those. Let me remind you how makefiles look. By the way, you can make comments in a makefile. That's the number sign. It's like a Python comment. You've learned Python before. So this is a makefile comment. This is not a CPP file. This is just a file called makefile with no extension. And so remember that every rule looks like the following. It's always the name of a target, the thing that you're trying to get, colon, and then you space separate all the ingredients to make the target. Ingredient 1, ingredient 2, as many as you need. And then you tab over, eventually. A bunch of tabs. And then you give all the terminal commands to, like, create, to make the target. It's all at the same indentation level. Make the target from the ingredients. At least in this class, you're only going to need one line in the body there. But that's how they look. And so, okay, let's give some rules. So I know that I want to make like the .o files. I want to do that efficient separate compilation with the G++-C. So I would like, for example, a target called main.o, right? I want a target called main.o. That's something I want to create. And all right, what do I require in order to create main.o? What must exist? Well, I need a main.cpp. So that's my ingredient to create it. And then I hit enter. Vim is auto tabbing over for me. And what do I do to create main.o from main.cpp? I will do the G++. G++-C, name of the file. All right? And that's the rule. That's it. Okay? Does that kind of make sense? Target, ingredients, recipe. Yeah.
Is there a reason why it uses the hashtag comment system? Is there like a convention? Is it like
No, actually, I would say that this comes from not Python. This is way before Python. I think it has to do with, have you heard of something called a shell script? It's a file similar to this that runs a bunch of terminal commands. Their comments are also number signs. So I would say that that's the original, and then I'm not sure why they decided on for shell scripts, but that's just like, I mean, it's easier than typing 2 slashes, one less key. But yeah, good question. So that's my rule. I need another rule for the other .o file, for searching.o, right? So I'll do the same thing. Searching.o requires searching.cpp to exist, and to make the final thing, I'll just do the G++-C again, okay? And then finally, I need one more rule, right, to link them together once the .o files exist. So I want some final thing called, I forget what we called it. We'll call it main this time, let's say. So main is my target, my final target, the thing I really want. And all right, what are its ingredients? What do I need to exist in order to create that thing, that main file? Well, I need both .o files to exist, main.o and searching.o. And if they do exist, like what's the recipe to build the main executable file from those? Well, it's G++, and then you link them together, right? Give both of these bad boys. They're guaranteed to exist, right? And then -o, call it what your target's name is main. Okay, so those are the 3 rules that that makefiles need. All right, does that kind of make sense? Are you ready to run the makefile? Let's watch it work together. All right, so in order to run a makefile, there's a terminal command called make. All right, so you say make space name of your target that you care about creating. So it's like, we'll do it very slowly. We'll do like make main.o. And so it hits it and it runs the rule. You see it printing out the thing that it did. And we now have main.o in my directory. Do the same with make searching.o. It runs this rule. It finds that searching.cpp exists. It makes that .o file. Then you do make main. It notices that both of those .o files exist, and it's going to run this rule. All right, run the body there, create a main executable that I can then go and run. Yay, and it runs. Okay, so that's all well and nice, but I told you that it's much better than that. So let me remove all those files, all the .o files, remove the main file. So just back to the code and then the makefile itself. If I say make main, this is where the beauty of makefiles comes in. If I say make main, it's going to notice that there are no .o files right now. I need those to run this rule. It's like, all right, no worries. I'm going to go looking for rules to make those .o files, and it finds them. So it's like, all right, I need main.o. I don't have it. Let me run this rule. Oh, I need searching.o. I don't have it. Let me run this rule. So I just say make main. I say the thing I really want, and it goes off and it does everything. Final executable. All the .o files exist. The final executable is there. Isn't that not beautiful? Just say what you really want and it makes it for you in the most efficient way. So if I go and I change something, if I go and let's add a line to main.cpp or something. Let's say I would like to binary search for something else. I don't know. What have I not binary searched for yet? The 42. So I've made a change to main.cpp. Do you remember what needs to be recompiled and relinked? So I never touched the searching library. Searching.o doesn't need to change. But main.o needs to be recompiled because I just added a line. Okay. And then I need to relink into main. So the makefile notices that. It's like, all right, you say make main. It's like, all right, I'm good on searching.o. It knows that. But main.o, it notices it's out of date. It's going to rerun that rule to make main.o and then relink them with the old searching.o as efficient as possible. It's tracking file modification times. That's how it knows. But it seems magic. You just say what you want. It's going to, in the most efficient way possible, compile it for you. I love it. All right. Any questions about that? That is makefiles in a nutshell. Yeah. Yeah, it's trying to be helpful and tell you, all right, this is exactly how I interpreted this rule. It's exactly what I just did right now. Because sometimes it's different, right? If I say make main again, make main. It's like, all right, I don't need to do anything. It's ready to go. So sometimes it does something, sometimes it does other things. Yeah, good question. So let's see, what else do I want to say? If you want to be as lazy as possible, you put the very first rule as the one you really care about. Because then if you just say make, it'll run that one. So if I just say make right now, it's going to run this one, which is kind of useless. So let's put the most important one up top here. The very first rule in the file can be make main. And now I can just say, let me remove some stuff. Remove the .o files and main. Now we're back to a blank. Clean slate. Now I can just say make, and it will run the rule to make main. Look at it go. I can run it. Everything's gorgeous. All right. So yeah, the first rule is usually the most important one that you put up there. Is that a question? Yes, you can though put multiple makefiles in each subdirectory too. You can call off to those if you need to. So there's a way. There's a way to use the subdirectories as well. But you might have to make multiple makefiles. Good question. All right. Any others? I think that's what I wanted to show you. Yeah.
More than one program.
Oh, for sure. Yeah, I can make some other program with some different, like, foo.o or whatever. You can have a bunch of different rules, and how to make, like, main2 from foo.o and some other things. As much as you want to do, you can put in here. 2 different thoughts if you need to. Good. Because, yeah, it's kind of a place to put a bunch of terminal commands. That's all a makefile really is. with some names associated with them. Good. All right. So yeah, that's going to be useful. I'll probably give you one in a future lab. Now you know how to use it. But I'd like to switch gears now. Let's talk about complexity some more, because you just need to know, right? We want to get good at writing efficient programs. And just like I kind of said last time, this is more of a CSCI 41 concept. It's very important for you to understand still, but it's kind of like getting ahead of the game. So I'm not really going to test you too much on this stuff. I promise that if I test you on anything, you can come back to these slides and read off the answer. All right, that's my promise to you from this little subsection on complexity. All right, so let's try to count. Remember, we were counting those basic operations that kind of gave us a number that told us how like fancy, how complex a program was. Let's count those basic operations for linear search and binary search, because I told you like one's way better than the other, right? Binary search blows linear search out of the water. Let's quantify that, okay? So remember that basic operations are this, right? Let's do it this way. I need bigger pens. Give me a second. Boop. And there we go. So a basic operation looks like this. All right, we're going to count these things, basic operations. It's an assignment, arithmetic, condition checking, anything that's simple like this. So like if I say int x equals 5 plus 2 or something. So you got the plus, that's one basic operation. It's going to make the 7. It's going to shove it into a place in memory called x. So there's 2 basic operations in this line. Does that come back to us? 2 basic operations. And we can count those. All right, so like we want to count like how many basic operations are there if I call linear search. Linear search on some vector for 42, right? What is that number? Okay. And coming up with those numbers, remember, is going to tell us, like in a mathematical, quantifiable way, how fast our program is going to be on any random processor out in the wild. And we're going to need a variable, though. Our algorithm analysis today is going to depend on a variable for sure. We're going to call it capital N. That's going to be the size of like the vector we're searching through. Because you know linear search is going to take longer for longer vectors, right? If you're searching linearly through this vector, it's not going to take you too long. But if you have like a size 1 million vector, it's going to take all day, maybe, right? You got more things to search through in the worst case. It's not like the first thing. See that? So we usually also care about the worst case as well. So let's go through the linear search algorithm. Like I've got it here. I've reproduced it on the slides in a kind of a similar way, but here's like the code, right? It's iterating, it's doing all that stuff. Here's the code in a smaller way. Let's count the basic operations for linear search. All right, let's do it. So like you call it, you're plopped into the body. What happens? All right, let's remember that n. Let's use n as our size of our vector. All right, so we'll say that v.size. If you ever see that, we'll call that n. There. Okay. So now I need to count. Now I need to count all these basic operations. Try to do it in your head with me. Tell me if I mess up. But we're going to the body here. Let's do it. So, okay, we hit a for loop is the very first thing. We got to remember how a for loop executes. Well, it's just this line once, right? That one's only going to happen once, and that's one basic operation, that assignment. It's already a value. And then we're repeating all this stuff, right? Everything but the initialization. So now we got to count those. So, okay, v.size, let's say, like, to go and ask the vector for its size, that's one basic operation. Let's pretend it is. More or less is. And the less than, once we have the size, compare it to a variable. That'll be another basic operation. And then we hit the body, right? The body and then the increment. So the body, so in the worst case, like, we got to run all these lines, right? So, okay, we got to go somewhere in a vector. Let's pretend that takes one basic operation. I'm shoving some things under the rug, but that's okay. Pretend that takes one basic operation. This is already variable. And then to compare the two things, another basic operation, okay? And then in the worst case, you're also going to return, right? You're going to run this line too. Let's say that that's the third basic operation for the body there. And then finally, the I++. Remember, it's secretly I equals I plus 1. So there's a plus. Got to do the plus as well as the assignment. So there's secretly 2 basic operations going on up in there. And yeah, I think that's it. And then we count this line down at the end once. Okay, that's one basic operation. And then we just got to figure out how many times this repeats, right? So I is going from 0 to size minus 1, and so that's exactly size times, right? Exactly n times. And then one more comparison to stop us. All right, does that kind of make enough sense? And that's what's going to happen there. I don't know if I need green actually, but okay, let's count it down. So we got our loop initialization. Oops, loop init. That's one basic operation, just the I equals 0. And then we got to do something. We're going to repeat a bunch of stuff exactly n times, because n is the size of the vector. All right, so we're going to do n times how many basic operations? It's going to be, I guess I need to go back to white, don't I? So 1, 2, 3, 4, 5, 6, 7 in the worst case. I know you're only ever going to return once, but we're just going to do the worst case. Okay. An upper bound is what we're trying to get at. 7 operations, let's say. And then, to stop the loop, remember, you have to run that condition one last time. Notice that I was a little too big. It's actually equal to size now, so it'll stop. So we got 2 more basic operations for that last version of the condition. So 2 more ops there. And then your last return line, in the worst case, you get to there, right? And so it's 1 basic operation to do the final return. So that is the analysis. Now let's like sum them up, bring them all together. That's going to be what? 7n, 7 times n, plus 1, 2, 3, 4. All right, so that's like 4 plus 7n. Does that analysis make sense to us? If your vector is size n, in the very worst case, you're going to run that. You're going to take that many basic operations to get through and run linear search on the vector. Yes? That's the body count. That's how much was inside the body there. I counted how many basic operations to execute the body once, and then we're going to repeat it n times. All right. Any other questions? Does it make enough sense? So you can kind of see how, like, as the size of the vector grows, so does the amount of work in the worst case you must do to search through it for linear search. It's growing like a line. Cool. It's like y equals 4 plus 7x or something. All right? Now we're going to do the same for binary search. And that is more difficult of an analysis. Okay? I would not dream of asking you to do this on a test in this class, but you should be able to understand it as I explained it at least. All right? So we're gonna count the basic operations now for binary search. And this is going to get a little complicated. All right, so, okay. Set things up, at least. This is easy. Low equals 0, that's 1 basic operation. v.size, just to get that, that's 1 basic operation. To do the minus, that's another assignment there. We're good. And then we add a while loop. All right, so we're going to repeat this condition. I'm not sure how many times yet. We'll figure that out. But you got the condition, and then I'll just do this faster now. 1, 2, 3 there for that one. Go into the vector, compare, +1. Do the assignment, what else? Go to the vector somewhere else, less than, subtraction, assignment, and then just a return. That's 1 basic operation. So apparently we're repeating all of those arrows. We'll have to count those in a second. A certain number of times. And then in the worst case, we get down to here, right, and we return -1. Okay? So let's try to count these at least. So outside of the loop at least, we've got what? We've got like 3 things there, right? So 4 things up top before we hit the loop. That's 4 basic operations. And then inside the loop, I'm going to have to section this off. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right? 13 operations inside the loop. I'm not sure how much the loop is going to iterate right now. It was easy for the last one. It's like do blank times. We'll get back to that. Something. All right? It's 13 operations. Okay? And then in the worst case, right, we're just counting the upper bound, because you know you're only going to hit one of these if-else's anyway. Just upper bound, easy analysis, easiest possible analysis. Then you need the loop to stop, so you need to check the condition one last time to stop the loop. All right, so that's 1 operation, and then 1 more to return -1. All right, so 1 basic operation to stop the loop, and one more to return -1. Okay? So now the question is, how many times does this loop iterate? The hard question to ask, okay? You have to actually think about, like, what in the world is binary search doing? Because there's no, like, number, really, that's going up. There's an idea. Like, there's a size of, like, a search space, essentially, right? That's the thing that's changing throughout the loop, okay? So, like, at the start of your loop, this is the size, your vector was, like, your search space, you were, like, going through the whole vector, right? And you had still stuff to look through, so the body kept running. Because, like, that's what the while loop was doing, like, while the search space is valid. So how long do you have a valid search space? How long can you possibly have a valid search space? You're going to search in the middle of that, right? And then make a decision. You're going to go left or go right, right? And so you're always cutting, each iteration of this loop, you're cutting that vector in half. Then you search in the middle there, and you cut off half some more of that smaller search space. And as long as you have a valid search space with at least one element in it, you can keep running the body, right? Keep searching in the middle, looking, making a guess, and then checking that guess, and then chopping off half of your search space each time. So do you see how the question of how many times does that loop iterate becomes, how many times can I cut a vector in half and still have an element inside? Does that make sense? That's the analysis that we have to do. And if you think about it, it's a mathematical function that comes in play that tells you how many times you can cut something in half. It's the logarithm base 2. It tells you how many times you can keep on dividing in half and have something still left. It's like the opposite of the exponential functions. Like it's doubling each time in that direction, but it's dividing in half by each time in that direction. So like the logarithm is the inverse of the exponential, we say. But that's going to give us the answer. Does that make sense? You'll have to round up or something if there's decimals, but like it's do about log base 2 of n times 13 things. That's how many times you got to run that body, okay? Round it up, potentially. And so, all right, adding all that up, it becomes 6 plus 13 times log base 2 of n. And that's our analysis. That is how many basic operations for a size n vector it takes, in the very worst case, upper bound, to go through that vector and find something, or find that it isn't there. Okay? Are there any questions about that? It's a little complicated, but it's a very useful thing. We have two functions now, essentially. Two mathematical functions that tell us exactly how fast these algorithms are. All right? And now we can graph, more or less. We can graph these things and figure out which one's better. All right? So the secret is we want to imagine like horrible cases, like we're working with millions upon millions of elements, because we don't really care about the small cases. They're both equally as fast. All right, so let's kind of draw a graph of these things. Whee. So here's n, as n gets large, and then here's like the number of operations based on a vector of size n to search through. So linear search was this graph, right? It was 4 plus 7n. All right, that's what we had there. And so it looks something like this. Not to scale. That was your linear search graph. As n gets large, that's how much work you have to do, in the worst case, to search through it for something. And then binary search, 13 was definitely bigger, right? 13 and like the 6, those are bigger things out in front and like inside compared to 4 and 7. But, okay, maybe that means that it's going to be a little bit longer, more work at the start, but you know the graph of a logarithm, right? And how it compares to a line. It's going to flatten out, kind of, like if you zoom out enough. It's going to grow much, much more slowly, binary search. Does that make sense? And so this is like a graphical reason why you always want to do binary search instead of linear search when you can, right? In the end, it's better in the end. For like size 1 million vectors, right? We're considering very large n over here, large n values. Because usually in like a industrial setting, you're working with like billions of numbers at once, maybe, okay? And this is true even though those constants were different. Like we had what? This was 13 out in front of here, this was only 7. And so maybe for a little while, linear search takes a little bit less time, but like those are for small values anyway. It's going to be done in the blink of an eye. We care when n gets large. Does that kind of make sense? That's kind of why we care about this analysis, all right? So like, what I mean by that is just like plug a million in. It doesn't actually matter. Logarithm wins out even if this c was like a million. Even if this was a million, and if this was like 1 instead of 7, even if you did it that way. A horrible binary search, still logarithm though, and a super good linear search, even better than 7 out in front. Like, if you zoom out far enough, even with those constants, 1 million times logarithm will always win it. Win over 1 times in n. Logarithm is always, in the end, going to be a lot smaller. Does that make sense? That's the analysis, and that's how you think of it, okay? You can zoom out. You can find a point where binary search wins, even if the constant out in front of there is like a million instead of 13. It's always going to be better than just n, okay? So that's the secret, that's the analysis, and that leads to a kind of notation, just like understanding like these constants out in front didn't really do much for large n. It's called big O notation, Okay, it's a very common thing in computer science. You'll get very familiar with this in CSCI 41. And so here are the rules for big O notation. We kind of notice that, okay, first of all, these little things out at the end there, like the 6 and like the 4, those are meaningless when n is a million or a billion. So we're just going to like drop those, okay? So here's like the rules of big O. Like we noticed we had like what, 7n plus 4? We're going to only care about the highest order term and drop everything else, because as n gets large, nobody cares about a 4 anymore. So we're going to turn that into 7n. All right, that's a simplification, but it helps us analyze things quickly. And then we're also going to drop any constants out in front, like the 7. The 7 doesn't really matter. We want to be able to compare like the actual functions themselves. Like 2 different kinds of constants out in front of an n, those don't really, like they're all blown out of the water by a log. It's kind of the deal, right? So like we're going to turn that into, we're going to drop the constant 7 to just give us n, okay? And then you do something with an O and call it a day, okay? So we say, after we do that process, we say that linear search is big O of n. That's its time complexity, we say, okay? So that's the secret. That's how you do it. And it's a kind of a shorthand, right? We've come up with this very complicated analysis, and it's just like a simplification of that. It just like tells you at a high level how fast your function grows, because we've turned our complexity into like something that we can graph a function. Okay, so we're using it for algorithms and like the running time that it takes to get through them. But mathematicians came up with a syntax for other things too. Just like it's about the growth of functions essentially. Okay, so linear search. It looks like it was off by 1 here. I gotta change that. Same slides. So we went from like what, 7n plus 4 to 7n to n, right? And so that's kind of the analysis. Drop the 4, we don't care. Then drop the 7, doesn't matter, compared against a log. Okay? So, yeah, then we say linear search is big O of n, and we write it like this. And we also call big O of n linear time. That's another reason why it's called linear search. The complexity of it is the graph of a line. Isn't that cool? And then this one, I also did a bad analysis last time, apparently. We came up with, what, 13 log base 2 of n plus 6 for binary search. The 6 doesn't matter as n gets large, so you drop it. You got this now. And then the 13 doesn't matter because you're comparing this against like n's or n squareds or other things. So we don't care about those constants. So we're just going to like log base 2 of n is the final thing. Put it within an O. Right? We say binary search is big O of log base 2 of n. And we call that logarithmic time. Okay? So that goes to show why binary search is much, much better than linear search. We have a quantifiable way to explain it now. Does that make sense? Just like plug a billion into both of those and see how much better binary search is. Won't even take like 50 basic operations probably. Or sorry, the 13 makes it worse. But it'll be much, much better, I promise. Much, much better. So I think that's what I wanted to say there. Yeah, are there any questions about that? I'm not going to like test you on how I did this, but hopefully you kind of understood it. Okay? So that's what I wanted to do there. If you really care about your one machine, like this is where I'm going to run my program for my server or whatever, like I want to know exactly how fast it is in terms of seconds and not basic operations, you can always do CTime stuff. There's stuff in the CTime library. It's called profiling your code. You can just like have a little virtual stopwatch inside your code, and here's how you do it. In the CTime library, in addition to being able to check the time, you can do this. Where is it? You can take time. So you can say there's a function called clock that kind of like looks at the virtual clock inside of your computer, and it gives back something called a clock t, which is like how many seconds-ish have passed since, like it looks at the number on the clock essentially. And what you do is you call clock twice. In between, you put your fancy algorithm that takes a few seconds or whatever, an hour. And so it's just like looking at the clock twice between those two times, between your fancy algorithm being run. And if you just subtract the n minus start, that gives you a number that can be converted into an actual amount of time. Whatever a clock t is not something normal. It's an integral value, first of all, so you got to static cast it. And then there's, in the library, they give you a little constant called clocks per second to turn clocks into seconds. And so you just got to follow this guide, and it will give you the number of seconds that it took to run your program, if you really care about that, all right? But usually most people are going to do this kind of analysis. Do the big O, count the basic operations, simplify it, call it a day, right? But if you need to, now you know how. I think that's what I wanted to say there. Are there any questions about any of that? Before I switch gears, I think one last time. All right. So the last thing I want to say is I want to talk about sorting algorithms, because like we're talking about algorithms and their analysis. Again, I'm not really going to test you on this. It's more of a CSCI 41 concept, but it's good to understand them, right? So, okay. I want to start with a question, because you guys have sorting algorithms in your mind already. You just don't know what their names are, maybe. But I'd like you guys to come up with an idea. All right? You don't have to write this down, but I will stop the attendance after I do this. So make sure to do attendance if you haven't already. But here's the setup. I want you to come up with an algorithm. Okay? Pretend that I have these numbers, and I tape like a bunch of like sticky notes onto the whiteboard or something, each with a number. The 18, the 23, the 12, the 8, or like I make magnets with those on them or something. I put them in that order. Of course, they're out of order. How would you take this list or these sticky notes or those magnets and move them around in the most efficient way to end up with a ascending list that's sorted? How would you do it? Like I'd go for this one and I'd drag it this way. Like can you describe it to your neighbor, right? That's going to be a sorting algorithm. See if you can figure out which one you would do. And just as a fun idea, like most humans would naturally choose one of these two algorithms that I'm about to give a name for and explain. Okay, but you try first. Convince your neighbor, like this is what I would do. I'd go looking for the 23 and move it over here or something. Like I could see all these numbers at once. Try to come up with a sorting algorithm in as much detail as you can. You don't got to write it down. Just like talk it out then. Okay. What would you do? Is there a number you go looking for first? All right, our conversation seems to be dying down. I'll give you another few seconds to talk it out. Can you articulate it? All right, we're getting quiet. Is there any brave soul who would like to share what they came up with? How would you all right, I got a bunch of papers in that order. How would you shuffle them around in the most efficient way? What would you go looking for? Any takers? What would you do? Yeah. Nice. Yeah, I think that would make sense. That's something I would totally do. Like, all right, go looking for the 7, right? Go and find the smallest thing. Like, okay, 7's got to be the first. Then 8's got to be the next thing. That's totally an algorithm. Anybody else come up with a different one? There's other ways to do it. Yeah. Okay.
And then we can store the max in its location. So once we look through it all first, we're going to move say wherever the minimum
Okay, yeah.
and switch that with the start. The maximum value was we switch that with the end.
We'll do both at once.
Yeah, and then we're going to keep looking at but take off the starting and ending values.
And then you have two smaller things to work with rather than one small. I like that. Going with both ends. Going for both ends. Awesome. So I would say that both of those ideas are plays on the idea of selection sort. Okay, there's another called insertion sort, and that's kind of how you're playing Uno or something, you're trying to sort your cards. That's usually what you do instead. But selection sort is probably what most of us thought of. Okay, so let me teach them to you. I'm excited. Okay, so there's some websites where there's some cool visualizations. I know your book has some cool stuff too. I promised to stop that. That's right. I'm gonna go to this website. You can just search for sorting algorithm visualization. There's plenty more where this came from. Here's a vector, essentially an array. You got the numbers in the vector in their order down here, and there's a bunch of different buttons for different sorting algorithms. And you can see like the relative size of the number is how big this bar is. So like once the sorting algorithm is finished, you should see like the bar is increasing. Okay, that's the goal. So I'm going to show you a bunch of different sorting algorithms, and this is called pseudocode, by the way. This is not really C++ code, but like you could translate it into C++ very easily. It's like it's taking a bunch of numbers, maybe as a vector, and then their size. So it could have taken it as an array. But the goal of every sorting algorithm is this. All right, it's always to do the following. If you had a jumbled vector or an array, it would translate it into the sorted one, just to make sure we're all on the same page here. This would get turned into 3, 5, 6, 7, 8. Okay. And the first one that I want to talk about is the dumbest one, but it's probably the easiest one to understand. It's called bubble sort. You never want to use this in practice, but it's a good first one to learn. Okay. So what it does, bubble sort, is all about swapping, and it's like really zoomed in on the array too. It's like swapping things that are only right next to each other if they're out of order. That's all that bubble sort is going to do. Okay. So like try to read this code as I'm trying to explain it here. But like, let me draw the original vector, this one up here. 8, 6, 7, 5, 3. The idea of a bubble sort is that you're zoomed in and you're looking very closely at your numbers, and you're just looking at things that are right next to each other. So you're going to compare these two guys, for example, the 8 and the 6. Oh, shoot. Can I do it like this? I want to be able to reuse this thing. There we go. So you're going to start, you're going to look at the 8 and the 6, you're like, are they out of order? And bubble sort's like, yes. So I will swap them. So, okay, this becomes 6, this becomes 8. And the vector is slightly more sorted now. Right? You see, if you did this enough, it would eventually become sorted. Then it moves on. All right, now on to the next one. Oh, man. All right, I got to just delete them. Now it's going to look at these two guys. It's like, all right, are those out of order? Yes. 7 and 8. Let's swap them. Just going to swap the things that are right next to each other. So now this is 7, this is 8. Okay? And now it's 8 versus 5. Are those out of order? Yes. So it'll swap them. 5 and 8. And then like, all right, 8 and 3. Are those out of order? Yes, it will swap them. So 3 and 8. That's the job of bubble sort. All right? And do you see how it's still not sorted? It goes 6, 7, 5, 3, 8 right now. But the 8 is in the right spot. If you play this game, you'll always move the biggest thing to the right. It'll keep winning out. See that? So I only need to sort the rest of these guys now. And I can keep playing that game. So I got to go through a slightly smaller and smaller array each time and play that game of swapping things, looking at things right next to each other. Okay? So in the worst case, right, it's all completely out of order. I need to go through a smaller and smaller vector n times the size of the vector times. Right? So that's what the outer loop is doing. It's going as many times as it needs to go. It's the worst case number of times you got to go through the thing. And then the j is a nested loop, of course. It's going to work on each pair. It's like, all right, which two numbers am I looking at right now? The j is like the leftmost one. So it's always working its way inwards, though. It's like number size minus I minus 1. Because it knows, like, I'm going to put something correct there in the end. And then here it is looking at the things right next to each other. J and j plus 1. If they're out of order, if j is bigger, I better swap them. So here's, you know how to swap, right? Temporary variable. So that's the job of bubble sort. That's as much as I want to explain it. But like, you can imagine that it's going to do the right thing, right? It's going to start over again on this smaller part. It's like, all right, we've got 6 versus 7. Those are in order. I can skip that. I'm good. Then now 7 versus 5, those are out of order. I better swap. And so now I've got what? This is 5. This is hard to see, sorry. 5, this is now 7. And now it's 7 versus 3. Again, those are out of order, so it's got to swap them. This is exactly what the algorithm will do. So now this is 3, and this is 7, and now 7's in the right spot. I never have to touch that index again. Now I'll just run bubble sort on this smaller array. Okay, just like that's what the loop is doing. That's why it's a nested loop. You got to go through the whole thing, all those pairs, a bunch of times, right? The amount gets smaller and smaller and smaller then. Okay, so the time complexity of bubble sort is n squared. Big O of n squared is like you're going about n times here and n times here, and it's like some constant number of work in the body there. You don't have to count it, but that's why it's n squared, and that's pretty slow as far as sorting is concerned. We can do better than that, but this is like the simplest sorting algorithm. All right, and so now I'm going to click bubble sort, and it's going to highlight the things that it's like looking at, and you'll watch it one by one move bigger things and bigger things to the right. Right, like it's comparing and swapping, comparing and swapping. You see that one that just keeps on moving. It's like that's the biggest thing, so far at least. It's making its way to the right. Boop. And so it's getting things slowly but surely. It has like this part is sorted. It's good to go there, but the rest, right? You got to work on the rest. And so some things like they're already close, like these big things are kind of close where they need to go. Like this small place, this number 10 right here. It's got to wait a long time to keep moving, right? It'll only move to the left if something bigger than it is to the left of it. Does that make sense? It's got to keep getting swapped and only move one place at most each round. So smaller and smaller arrays to work with, but it's still taking forever. See that? But that's bubble sort. You can understand that, right? Bless you. Any questions about that? These are fun little animations. I like them. So it's smaller and smaller and smaller, and it keeps like, all right, now it's in order. It didn't know that. No, it just had to try the worst case number of times. But now I've got a sorted vector. That's bubble sort, all right? And I can click randomize again to get ready for the next one. But that's the secret. As fast as the speed it will allow me to do it. Okay. Does that make sense? You think you could code this up? Could you translate this to C++? It's almost C++. It's very close. And that's bubble sort. Let's talk about a more normal one. Right? This is selection sort. That's the one that a lot of us chose and talked about. That's this sorting algorithm. All right. So let me draw a jumbled array again. Again, I have pseudocode. This is not C++, but it's close enough. 8, 6, 7, 5, 3. Boop. And so, what selection sort is all about is it's going to go and find the smallest thing, and you know that the smallest thing needs to go at the start. Okay? So it's like go find the minimum in the rest of your array, put it in the right spot. So like, all right, I'm going to fill in this index right now. Let me go find the smallest thing. Oh, it's the 3, so it'll swap. Swap the thing there with the smallest thing. All right? And then I don't need to touch this index ever again, do I? That's in the right spot. So now it'll go and it will selection sort this smaller array. See that? Trying to fill in the next location, so it'll go find the minimum here. What is that? Oh, it's the 5. So it'll swap the thing at that index with the minimum thing that it found. All right, so now the 3 and the 5 are in the right spot, and it can go and it can selection sort the smaller array there. Does that kind of make sense? That's what you would do with the papers, a lot of us. That's selection sort, and here's how you kind of code it, right? You got to like, all right, which index am I trying to fill in with the minimum right now? Starts at 0, right? Works its way up. And then you go and you look, right? You go and you look in the rest of the array. So there's another nested loop, right? Like I'm trying to fill in this one. Let me search and find the minimum in the whole array. Or I'm trying to fill in this one. Let me search in this size 4 array for the minimum right now. Okay, so it's like it's got to be another loop now, inner loop. Like starting here, let's keep on looking for the smallest thing. Find me the smallest index right now. All right, and then once it found it, once this loop is done, it knows where the smallest thing is in that array. It'll swap the index that it's trying to fill with the thing that is the smallest. Okay, and so again, it's a nested for loop. We've got this is going about n times. This is going smaller each time, but n on average, and it's doing some constant amount of work in the body there and like some extra stuff out here. So it's going to be n squared again. Right? It's still pretty slow, but it's significantly better. The constant out in front of that n squared is so much better than bubble sort. There's a whole lot less swapping, for example. I hope you can imagine, right? It's just like find the minimum, then do one swap, okay? So there's a lot, this is much more efficient, even though it's still big O of n squared, we say, okay? And so it's selecting the minimum each round. That's kind of how it's called selection sort, or why? So let's watch this one. selection sort. So you're going to watch it highlight its best guess for the minimum. Eventually, it will find the right minimum, and it will put it where it needs to go. There it is. It found it. It's highlighted. They're just small bars right now. It's placing them right there. See, its best guess for the minimum is that one. It's going to put it right there if it really was the minimum. And so it's not going to touch the rest of this array anymore. It's got to go through this one now, find the minimum, put it in the right spot. Find the minimum, put it in the right spot. So that's another approach to sorting. Does that make sense to us? Any questions about selection sort? Think you could code this up without seeing the pseudocode? What I care about is you understanding the idea, because you could. With enough time, I believe that you could. Once you got the idea, you know the rest. Okay, so that's selection sort. All right. The next one is called insertion sort. This one, finally, is a nested loop, but one's a for and one's a while this time. Mixing things up. All right, so let's do this one. Let me have my favorite jumbled array. What insertion sort is all about, it's like a competitor to selection sort. They're like the two big n-squared algorithms, the two best ones. What insertion sort is all about, instead of selection sorts like, all right, I'm going to find the minimum, put it right here, the thing that never needs to ever leave here again, I'm good. What insertion sort is about is it's going to make a locally sorted subarray, which is kind of weird to think about. What it's going to do is it's going to be like, all right, I'm sorting up to here. And it's going to make sure that the original elements up to there were sorted. That's what it's going to do. It's going to bring in a new one each time. Okay, that's the difference. It's kind of what you do if you have like cards in your hand, like I'm going to move this one over here, and the next one needs to go here, the one after that needs to go down here. That's kind of what you do if you're like playing Uno or something. Let's see. For example, if it's like insertion sort is sorted up to index 3, that means this part of the array will be sorted with the original 3 values, not the values that eventually need to maybe go there, but the original pieces of the array are in that sorted order. All right, it's not moving things outside. So the very first thing it does is like, all right, section off that array, just the array 8, that's already sorted, we're good. So it's going to move its frontier, we say, bring in the 6, and now it's going to move the 6 down to where it needs to go and keep this part sorted. So do you see how it's going to swap the 6 and the 8 there? It's going to move the 6 down, it needs to come before the 8. So all right, it's going to swap them, 6 and 8, and now I have this part of the array sorted. All right, with the original 2 elements, not what eventually needs to really go there, but the original 2 elements. Okay? That's the different thing that an insertion sort does. And then it's like, all right, those are sorted. Let's keep on trucking. Let's bring in the new guy. Bring in the 7 and get it down to where it needs to go. 7 needs to move to be in between, right? And so you'll do some swapping eventually and move the 7 here and the 8 here. And now you do have these first 3 elements. They are sorted. Does that make sense? That's what insertion sort is going to do. And then it will expand its frontier again. And like, all right, move the 5 down to where it needs to go, which is apparently at the start. All right, move it way down there. That's what it will need to do. And then I will have a sorted, like the first 4 elements are sorted. Like once you've gone through all of them, put them in the right spot, you have sorted the whole thing. Does that kind of make sense? That's insertion sort. So it's like, all right, if it's sorted up to index 3, then the first 3 elements of the original array must be in sorted order at that point. It's not moving things around from far away. Okay. This is still, though, going to be n squared. So here it is. It's got a loop. It's a nested loop. It's like, all right, where's my frontier right now? It's on index 1 up to n minus 1. And then it has another loop. It's like, all right, I've just brought in this new thing at index j. Keep on swapping it down until it's in the right spot. It's kind of bubble sorty, isn't it? It's like, all right, keep going, keep moving it down. And if the thing below it is bigger, because it shouldn't have been there, keep on swapping. There's a more efficient way to do this, but no, we won't consider it. Yeah, this is kind of how you have to do it. It's a bunch of swaps still, but maybe not too many if it's a big-ish number. Right? It doesn't have to move down too far, but you're going to put it in the right spot, and then eventually it'll be done. So that's a for loop and a while loop. This is going to go like n minus 2 times, and then this in the worst case is going to like keep on moving it down to the very start if it's backwards. So in the worst case, it's an n squared algorithm, but there's actually a best case that's better. The rest of these, like selection sort, bubble sort, they're going to take the same amount of time no matter what. They don't really care. But insertion sort has a different running time if the array is almost sorted or already sorted, which is interesting. So here's insertion sort. You're going to watch it. Like it's going to be sorted up to here, but there's going to be small things over there still. It's like only keeping track of a locally sorted array, bringing in a new thing one at a time down to where it needs to go. Okay, so you see the smaller things moving that way. They keep getting swapped. And so I think we consider insertion sort to be the best n squared sorting algorithm because of that best case. If the array is already sorted, or very close to being sorted, it's just a little bit jumbled, you won't have to move that new thing that you bring in down very far, will you? And so you don't have to move it too many times. It means like a constant number of swaps, or like a linear number of swaps. And so that ends up going to a better running time. So like that one's going to move down, and it'll stop once it gets in the right spot. It doesn't have to go down all the way. Okay, so that's insertion sort and the difference there. And the best case of insertion sort is linear time. The array is already sorted. It's like, all right, expand the frontier. Where does this new thing need to go? Oh, it's already in the right spot, or it only needs to move down like 2 things. We're good. So it's just got to do a check. It's like, oh, okay, we're good. So it's faster. Cool. I think that's what I wanted to say about insertion sort. I think it's the king of the n squared sorting algorithms. Well, we can do better than that. Are we ready to learn better ones? Fancier sorting algorithms. All right. So sadly, or maybe not sadly, for me, I love that I get to teach this, but maybe you hate recursion. The rest of them are recursive. So again, you need recursion to do something cool and make a better sorting algorithm. So the 2 algorithms that I want to show you, the kind of like the cream of the crop for sorting, they're called divide and conquer algorithms. That's how they're defined or described. And a divide and conquer algorithm does not have to be a sorting algorithm, but these ones are. A divide and conquer algorithm, just in general, is one that is both recursive, so it has to be recursive, and then also you're splitting up the problem evenly, like in halves, or like in thirds, or in quarters, or something. And each piece that you can go and work on separately, they're not going to overlap. Okay? So that's what it means to have a divide and conquer algorithm. Your problems split evenly, don't overlap, and it's recursive. All right? And so just like keep on breaking it down until you hit a base case. And then you're good to go, and you build up the answer from the recursive cases solution. So like here's one of the sorting algorithms. I can explain it to you recursively very quickly in a nutshell. 8, 6, 7, 5, 3, 0. Here's my array. Usually when you're dividing and conquering, usually you're cutting something in half. Usually that's the normal number, not just like thirds or something. So like, okay, we got this array. I want to sort it fast with a divide and conquer sorting algorithm, so I'm going to cut it in half. I'm going to work on this array and this array. See that? And so I'm just going to say, all right, these are smaller arrays, aren't they? So I can recursively hand off this to the sorting function. My recursive divide and conquer sorting function. I get to assume that this has made 6, 7, 8 for me by the power of recursion, don't I? And then this guy, all right, I'm sorting that, 0 through 5. I get to assume that recursion gives back to me a sorted version of that smaller array because it was smaller. It will, if I build it back up correctly, if I do the answer right, it will have worked. It will actually have done that. And then, all right, I have these 2 sorted things. I need to kind of like bring them back together, don't I, into the final sorted thing. And that's a very quick thing. That's a very quick thing to do. It's like, all right, you're just comparing. This is not to scale, is it? 2, 3, 4, 5, 6. It's like, all right, 0 versus 6, 0. 3 versus 6. It's always like the smallest thing versus smallest thing. It's like, it's easier that way once it's sorted. 0, 3, 5, 6, 7, 8, I guess. That will be how we combine our smaller answers. So we divided, we conquered, right? And then we built back up, essentially. That's a divide and conquer algorithm in a nutshell. So the one that I just explained to you, that this exact drawing, that's of an algorithm called merge sort. It's called merge sort. So what it does is it's actually 2 pieces. There's the original merge sort function, and then there's a helper function called merge. Look in your book for the actual pseudocode or the implementation. It's there. But I just want to explain it in picture form. 8, 6, 7, 5, 3, 0. Whee. What you're going to do is you're going to cut your array in half, or your vector in half, and you're going to recursively call merge sort on those 2 smaller arrays, right? It's like merge sort up to these indices or up to these indices. And so you get, just through the magic of recursion, it'll make its way to the base case, figure it out for you. What's the base case of sorting, by the way? It's like you're sorting a size 1 vector or size 0 vector. It's already sorted. 6, 7, 8. You get to assume this will give you back the right answer for the smaller call, 0, 3, 5. So that's what merge sort is. You call merge sort on the smaller things. You got that answer back. And then what do? You merge them back together. So there's a helper function called merge that takes both of these pieces and puts them where they need to go in the original vector. All right. You do need a little bit of extra space for a split second to do the merge process, but then you can copy it back into the original place. All right, so here's the merge process. It's like, all right, I got these two sorted smaller things. I need to bring them together. I need to merge them together into a final sorted thing still. And so you just like put pointers, not pointers, but like indices on both of those. Not supposed to be a 0, by the way. 0. And it's like, all right, now it's 0 versus 6. Which one wins? See, that's a very fast process. Like, all right, the 0 wins. Now it's 3 versus 6. Who wins? 3. Now it's 5 versus 6. Who wins? 5. Now I've exhausted the whole right side, so I'll take all of these, the 6, the 7, the 8, and then I'm done. So you just bring them down in there. You merge them together, right? Boop, boop. And so that's a fast thing. That's like, you can imagine it's like a linear time thing. You got to visit every index in order. So that's not too bad. And yeah, that's the secret. You do that separate array, this green one, to do the merging, then you copy it back into the original one. That's what you have to do. Try this and you'll learn why. You can't do it in place. But the power of divide and conquer, like I keep cutting in half, cutting in half, cutting in half, just like binary search kind of did. I get a logarithm instead of an n. And so one of those n's, instead of n squared, n times n, one of those n's turns into a logarithm, because that's how far down I can cut in half a vector and still have something left. That's kind of why, in a hand-wavy, nutshell-y way. But this turns into n times log base 2 of n running time complexity, okay? With some constants out in front. And that's significantly better for large n. You know that log beats n much better, right? It's much, much better to do this one for large n, and that is optimal. That's about as good as you can do, actually. N log n is as good as you can do for sorting. We've proven it for generic sorting algorithms, all right? You can do slightly faster for like certain numbers, but like in general, you cannot do better than n log n. Merge sort is a top contender, right? So random array. What merge sort is going to do, it'll have its helper copy down here, but it's going to recursively call merge sort, right, on those smaller pieces to recursively sort them and eventually merge them back into the original place. So here it is, like here's what the recursion is dealing with right now, and you saw it just merge them back. Merging. So now it's got the left half of the whole thing is sorted. Now it's working on the right half recursively, sorting, merging, copying, and then merging one last time. And I couldn't, like I ran out of, like it was done before I could finish talking. That's n log n for you. Significantly faster, right? Are there any questions about that? So that's merge sort in a nutshell. The code is in your book. I don't want to get into the code too much, but like the idea of the recursive case is what the drawing was all about, okay? So that's a good one to know. Yeah, if we're happy, there's one last one, and this is like the best one. This is called quicksort. They called it that for a reason. It is the best in general sorting algorithm. It's also going to be n log n. Can't do better than that. But the constant out in front is, in practice, better than merge sort. So people prefer quicksort in general. And again, I'm not going to give you the code. Look at it in your book. Go on the internet, watch videos. But there's two functions again. There's the original quicksort function, just like merge sort had merge. Quicksort has another one called partition. All right, and that one actually works first. That one happens first. Second. So what happens in partition, I need a very carefully arranged array to show you. Let's say that our array is in this order. 5, 8, 0. No. 5, 8, 7. 3, 0, 4. Alright. So I did it this way for an illustrative reason. So let's say this is my original vector or array that I'd like to sort with quicksort. What it does is it calls partition first. And what partition's job is like these are new terms, new terminology. Partition picks one of the elements and calls it something special. It's called a pivot, and it's going to pivot the array around that element. All right. So let's say that we've chosen, just like randomly, we've chosen that 5 is going to be our pivot value. All right. And now the job of partition is it's going to move everybody else around the 5, essentially. It's going to make sure that everything to the left, on the left side of the array, is smaller than the pivot, and everything on the right side is bigger than the pivot. Or like it picks one of them if there's equals and stuff. But that's kind of it. Smaller things to the left, smaller things than the pivot to the left, and bigger things to the pivot than the pivot to the right. Right? And so here's kind of that process. It's like, okay, I'm going to pivot around the 5 for the rest of these guys. So I'll start an index over here and an index over here. And all right, I've got an 8 is not on the right side. It needs to move over. It's bigger than 5. It needs to be on the right side of the array. And then the 4 also, right? It's on the wrong side of the array. It's smaller than the 5, so it needs to be moved to the left. So like, all right, I got 2 things in the wrong spot. I'll swap them. So now we've got 4 over here, 8 over there. And now those are in good spots. They're on the right sides. So now I'll move inwards. So now it's going to be 7 versus 0. The 7 again needs to move to the right. It needs to be on the right side of the array. It's bigger than the pivot. And then the 0 also needs to move to the left. It's smaller than the pivot. So again, those need to swap. 0, 7. And then you meet in the middle, kind of. And that's when you're done, more or less. So now you have 4, 0, 3 over here. You see that? 4, 0, 3 over here. And 7 and 8 over here. So like things smaller, things bigger. And then actually where they met is, if you think about it, this is actually where the 5 needs to go, isn't it? If you just swap the 3 and the 5 one last time, 3 with the pivot value, the 5, this is in the right spot. I never need to touch that. And let me draw that in a different color, actually. It's like that's a key piece, all right? It's like, okay, I'll swap those. 3 here, 5 here. And now I never need to touch this index again. Because like everything to the left is smaller, right? Everything to the right is bigger. So by definition, the 5 is in the right spot for sorted order. The rest of the array is still jumbled a little bit. But the 5 never needs to move ever again. Does that make sense? That's what quicksort is going to do. That's the partitioning process. And now I have 2 smaller arrays, don't I? Slightly smaller than merge sort even, because like this pivot's already in the right spot. I don't need to touch it. So that's kind of why quicksort's a little bit better maybe. So now I got these 2 smaller arrays that I can recursively call quicksort on. All right, that's the secret. 2 smaller arrays, it will work. All right, so that's the idea. So again, it's going to partition with respect to a pivot element. Put that one in the right spot because that's what happens, right? When you partition, and then you got 2 smaller unsorted subarrays. Then you will call quicksort on both of them recursively. They're smaller things. The magic of recursion takes over, and it's going to sort those things. All right. So that is the secret. And as long as you have a good pivot, if you choose a random value, it's always going to work out very well on average. As long as you can have the pivot partition the array in 2 equal pieces, then you're going to get n log n. Again, it's cutting it in half. Okay. You may, though, quicksort has a worst case. It's very hard to get the worst case, but that you could keep on choosing a horrible pivot element potentially. We're like, all right, everything to the left is over there, everything to the right is right there. It's just like one value. Do you see how if it did it that way and it kept doing it that way, like, oh no, I have to sort all this again. Now I have to sort just all this. Like giant arrays each time. That turns into n squared. It's like if you pick a bad pivot element that does not chop in half, then you're not going to get the logarithm goodness. Okay, is that a question? You wanted an 8 right here to start? Oh, you do need to play a bit of a carefuler game. I still have to some things under the rug. Yeah, then you have to move left one. Is that your question? Yeah, you do have to be a little careful. So it's where they meet, and then you have to play a little game. Like, am I in a good spot right now? You'll move the indices in a way that gets you to where the pivot should go. Yeah, good question. But it's just like you move once or something. It's not too bad. Yeah, so that's quicksort in a nutshell. Are we ready to watch it work? And so what this particular visualization is going to show, it's going to show you the pivot element as a line. It's a straight line. It's like everything above the line, all those values are going to the right. Everything small on the line is going to the right, going to the left. And so quicksort does not. Also, it saves some space. It's going to work inside the array itself. It doesn't need an extra piece of anything. And so here it is. There's the pivot. Everything to the right. It's about halfway, so that's perfect. See how everything to the right is bigger? And everything to the left is smaller. Now it's recursively sorting the smaller and smaller arrays. Choosing some pivot elements may or may not be good. I don't know. So it's partitioning and quick sorting. Partitioning, quick sorting. Smaller and smaller things. Eventually, everybody's going to get in the right spot. And so that is the secret. That is quick sort in a nutshell. It's a good one to remember and to memorize. If you go and you find the code on the internet or in your book, look at the diagrams long enough to understand it and to learn it fully. Okay? But I think that's all that I wanted to say about it today. I gave you a little sneak peek of it at least. Any questions about any of the sorting algorithms? So I think that's the end of it all. Yeah. How long is the worst case scenario? Oh, that becomes an n-squared algorithm at that point. So it kind of like becomes selection sort or something. Becomes insertion sort. You can think of it that way. Yeah. But you usually don't hit the worst case if you choose a random pivot, because then it'll always, on average, be halved each time. Yeah, good questions. All right, I think that's all that I wanted to say today. Let's confirm that. Yeah, it's just going to be the lecture, so the rest of the time is all yours.